lands a little bit later. In terms of what happens to AirSat-1 after that, there is then separation. That is going to happen in orbit. Antennas will deploy, and then we will come back here a little bit later on for AOS, or acquisition of signal. If you have no idea what that means, don't worry. I have people here who are going to explain that to you over the course of the evening properly. We'll find out all of that throughout the course of the evening as we are here. Now we're on our way towards lunch. My guests are with me here for most of the evening. Maeve Doyle, Maeve, tell me about your role within all of this.
So I'm a former AirSat-1 team member. I worked on the project during my MSc first and then my PhD on the flight software and operations for the mission. Okay,
Alex Kinnaird, what has been your involvement in all of this?
Yeah, so I work at the European Space Agency in the Education Office, and we have a program called the Flyer Satellite Program, of which I'm the program coordinator, and this program is in support of university CubeSat satellites like this one.
Okay, Maeve, somebody has switched on just now, has absolutely no idea what is happening other than that Ireland is launching its first satellite tonight. Just take us back 6 years and maybe explain to us the story of AirSat-1.
Yeah, so I suppose AirSat-1 really got started because of the interest of a research group here in the School of Physics at University College Dublin called the Space Science Research Group. That research group are very interested in an astrophysical source known as gamma ray bursts, or GRBs, and the high energy radiation that they give off. So as part of that interest, they were looking into the development of detector technologies, miniaturized detector technologies, as part of ESA contracts prior to the FYS programme. But then when the Flyer Satellite 2 call came about to have university class projects potentially launch these miniaturized satellite platforms with a payload on board, it very much piqued the interest of the group.
I bet it did. How did you get involved yourself personally?
It was a little bit of right place, right time. I was doing a research master's with the group at the time that AirSat-1 was accepted to the Flyer Satellite Programme.
And given that it's been 6 years, it's not just a single group of students who've been involved with this. There have been a lot of people over the course of the last 6 years. How many are we talking, roughly?
About 50, I think, in total. So the project, as you said, was 6 years long. A typical master's programme is 1 to 2 years. Typical PhD programme is 4 years. So we've had a lot of students contributing to the project, not just from the School of Physics, but also from schools in engineering, mechanical and materials engineering, schools of computer science, and the schools of maths. So everyone bringing different skill sets and knowledge to the table.
And now we are this close to launch. How does that feel?
It's amazing. Yeah, kind of unbelievable.
How do you begin a project like this? So when you were accepted and you thought, okay, we're going to build Ireland's first ever satellite. You have no expertise in this. There's relatively little in the country. What happens when you're building that from the ground up?
So as I said, there's a lot of different students with different backgrounds. So you need a lot of people with bringing different skills to the table and different knowledge sets. But you also need a lot of support from the Flyer Satellite Programme in this case. So yeah, the Flyer Satellite Programme was essential to us. Okay,
for everybody who's wondering what the metal Battenberg is here, I'm going to just put that slightly in that seat. Metal Battenberg here is in front of us. This is a scale model of AirSat-1, which is about to be launched in a little over 13 minutes time. Maybe walk us through exactly what it is that happens when AirSat-1 actually gets out and starts doing some science.
Yeah, so when AirSat-1 will be deployed later on orbit, it will power on first. So that's the first thing it does when it really comes out of its deployer on orbit. It'll gather some health check data, just start logging that for us to acquire later. But most importantly, it'll start this 45-minute wait timer, and that 45-minute wait timer defines when we can release the antenna elements from the spacecraft from the bottom here. And those antenna elements allow us not only hear from AirSat-1, but also to be able to talk to it, which is essential for us to acquire that first signal, that first two-way communications.
And maybe talk about the experiments on it as well. Just show us through where everything is on the actual satellite itself.
Yeah, of course. So AirSat-1 is a CubeSat. So CubeSats are defined in units of 10 by 10 by 10 centimetres. AirSat-1 is a little bit larger than that because it's a 2U spacecraft, so 2U stacked on top of each other. It's a small spacecraft, but a lot of capabilities packed in. The first of which is a gamma ray detector. So we have the solar panels removed from two sides of this model here so that we can see inside. And we can see GMOD, which is our gamma ray detector, which is going to be used to study the high energy light from gamma ray bursts. The second payload is on the exterior of the spacecraft. It's called the EMBIO module, or EMOD. So that's a thermal materials experiment. And the third payload I can unfortunately not point out because it's a software-based payload. And that's going to control the orientation of AirSat-1 on orbit.
Okay, Alex, we're talking about 120 experts at ESA that have been supporting this?
Yeah, really a lot of experts across all the directorates of ESA. So one of the big parts about the Flyer Satellite Programme is that we try and have the experts that are doing other satellite projects, I say real satellite projects, but this is a real satellite project, doing big ESA missions in touch directly with the students. So they're transferring that expertise from ESA technical people, engineering people, to the students directly.
Okay. One of the things that interested me most when I was reading up about this was legal support is something that the team needed, because laws have to be created here in order for this to happen.
Yeah, so as I said, it was really
Falcon 9 are ready for liftoff with our 25 rideshare payloads on
T-minus 30 seconds. T-minus 15 seconds. T-minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Ignition. And Falcon 9, go Korea 425, go SpaceX.
Vehicles pitching downrange.
It is a beautiful day for launch, and Falcon 9 has successfully lifted off from Vandenberg Space Force Base with payloads for 6 of our rideshare customers on board: Korea, Space BD, Citael, D-Orbit, York Space Systems, and Planet IQ. Now, during ascent, we tilt the engines. The technical term for this is gimbaling, and that turns the rocket horizontally in what we call a gravity turn. We're still going up, but now we are also heading horizontally away from the launch pad.
Max Q.
There's the call out from Max Q. So moments ago, we throttled engines down in preparation for Max Q.
Nominal.
Good call-outs there that power and telemetry are nominal on board Falcon 9. Max Q is a critical moment during flight because the combined stresses caused by Falcon 9 accelerating through the atmosphere and the ambient static pressure are at their greatest. Now, the rocket typically needs to go around 17,500 miles per hour horizontally in order to avoid being pulled back down to Earth and reach orbit, which is why we perform that gravity turn. You can track our progress to orbit by keeping an eye on the Stage 1 telemetry in the bottom corner of your screen. Now we have 6 events coming up in quick succession: MECO, Stage SEP, S1 Flip, SES1, Boost Back Burn, Start, and Fairing Separation. During main engine cutoff, we'll shut down the 9 Merlin 1D engines, which is followed by stage separation.
Nominal trajectory.
Nominal trajectory on board Falcon 9. Once separated from the second stage, the booster will flip its orientation and begin heading back to Earth with a short boost back burn, while simultaneously the second stage MVAC engine will ignite for the first time, followed quickly by fairing separation.
MECO. Stage separation confirmed.
Confirmation of MECO and stage SEP.
And back ignition.
Good call-outs that we've had
Stage
SES1
boost back startup.
and boost back burn startup.
Fairing separation confirmed.
So we've heard those call-outs for those 6 events that happened back-to-back and got great views of several of them. That was MECO, Stage SEP, S1 Flip, SES1, Boost Back Burn Start, and Fairing Separation. We will be attempting to retrieve those fairing halves again today once they fall back to Earth, using our recovery vessel, Go Beyond. Next up, we're listening to hear that we've completed our boost back burn.
Stage 1 boost back shutdown.
Right on schedule. We are just about T plus 3 minutes and 28 seconds into today's mission, and the next critical milestone we're tracking is T plus 6 minutes and 42 seconds, when we expect to have some great views of the first stage's entry burn. For the entry burn, we relight 3 of the M1D
Both vehicles
engines.
remain on a nominal trajectory.
There we hear that Falcon 9 remains on a nominal trajectory. For the entry burn, first we will relight the center E9 engine, followed shortly after by E1 and E5, which slows down the vehicle as it passes back into the Earth's atmosphere. Great views on your screen right now of stage 1 and those grid fins as the booster heads back to Earth. We relight those engines to slow down and reduce re-entry forces, which ultimately helps us recover and reuse the first stage. During the entry burn, Falcon 9 is decelerating by firing those Merlin engines, but we're still moving really fast. This causes the vehicle to fly through Merlin's exhaust gases, also called the rocket's plume. And this deposits a layer of soot on the vehicle's surface, which is why our flight-proven vehicles tend to look so toasty. That soot comes from the carbon-based fuel that Falcon 9 uses. Now, as a quick reminder, at the request of some of our customers, we won't be showing any views of our payloads today. Live coverage will end after the first stage landing and successful shutdown of MVAC's first burn. Just about a minute and a half until we expect to hear the call out that that entry burn has begun. Those grid fins on your screen are the primary mechanical mechanism that we use to steer the booster on its way back to Earth. Interestingly, even though they look quite small next to Falcon 9, they are about 4 by 5 feet, so about as large as a coffee table. Of course, we reuse our boosters and fairings here at SpaceX because reusability is a key to lowering the cost of spaceflight, which enables more investments in critical scientific research. Again, the Falcon 9 first stage supporting today's mission is about to perform this entry burn for the 17th time. Great views of the coast of California beginning to come onto your screen now.
Stage 1 entry burn.
Confirmation of entry burn startup. On your screen right now, you have 2 views of our first stage, one from our onboard camera on the left, and on the right-hand side, you can watch that landing as we come back toward landing zone 4 at Vandenberg Space Force Base.
Stage 1 entry burn shutdown.
Confirmation of entry burn end.
Saved.
The Merlins on board the first stage are optimized for sea level. These achieve about 190,000 pounds of thrust during both ascent and descent, while the MVAC engine is optimized to operate in space, producing 220,500 pounds of thrust in vacuum. Coming up next, we'll shut down our MVAC engine on the second stage, followed quickly by our landing burn on the first stage. And as a reminder, we are targeting a land landing at landing zone 4 at Vandenberg Space Force Base today, which is just west of our launch pad.
Stage 1 transonic.
Stage 2 FTS has saved.
Beautiful views
Stage 1
there,
landing burn.
and confirmation that we have begun our landing burn. We're now waiting for Falcon to land back at landing zone 4.
Stage 1 landing leg deploy.
And there you have it.
Stage
That
1
marks
landing confirmed.
SpaceX's 250th recovery of an orbital-class rocket, including first-stage landings for Falcon 9 and Falcon Heavy. While the mission isn't over just yet, as a reminder, we won't be showing any second-stage views today, and therefore we're going to end our coverage here. All of us at SpaceX want to give a big thank you to our customers, including Korea, Space BD, C2L, D-Orbit, York Space Systems, and Planet IQ for entrusting us with today's mission. For those of you interested in learning more about today's payloads and deployments, please head over to our customers' websites for more information. We also want to give a shout out to the Range and Federal Aviation Administration for supporting today's launch. Thanks to all our viewers for tuning in and for your continued support. We'll see you again soon.